Why you can't remember being born. You were awake. You were learning. Your brain was forming new connections every single second. And you will never, for as long as you live, remember one moment of your first 3 years on Earth. Not your first steps. Not the first time you saw your mother's face and understood, somehow, that this was the person who kept you alive. Not your first birthday, the cake, the candle, the singing. All of it happened to you. None of it stayed. Psychologists call this infantile amnesia, and it is one of the strangest gaps in human experience, because it isn't a gap in living. It's a gap in remembering something you definitely lived through. Sigmund Freud noticed it first, back in the early 1900s. He assumed the explanation was psychological. Something about early childhood, he theorized, was too emotionally disturbing to keep, so the mind buried it deliberately, the same way it might repress a trauma. For decades, that idea shaped how people talked about early memory. It sounded reasonable. It was also almost completely wrong. It took nearly a century of neuroscience to figure out what was actually happening, and the real answer has nothing to do with repression. It has to do with construction. Here's the first thing researchers had to rule out: the idea that babies simply aren't forming memories at all. That turned out to be false almost immediately. In the 1980s and 1990s, developmental psychologists ran a series of experiments using something called deferred imitation. Researchers would show infants as young as 6 months old a novel action, like pulling apart a toy in a specific sequence. Then they'd wait. A day later, sometimes a week later, they'd hand the infant the same toy with no demonstration at all. The babies performed the sequence correctly. They had watched once, stored it, and retrieved it days afterward. That is memory. Functioning, working memory, in a brain barely 6 months old. So babies remember. They just don't remember the way adults do, and the reason comes down to a structure most people have never heard of: the hippocampus. The hippocampus is the brain's memory indexing system. It doesn't store long-term memories itself so much as it catalogs them, linking scattered pieces of an experience, a smell, a sound, a face, a location, into a single retrievable file. In adults, a fully mature hippocampus can build these files efficiently. In infants, the hippocampus is still under construction. Specifically, a region called the dentate gyrus, part of the hippocampal circuit responsible for telling similar memories apart from one another, doesn't finish developing until somewhere between 2 and 4 years of age. In 2014, neuroscientist Paul Franklin at the University of Toronto ran a study on mice that helped confirm exactly what this immature circuitry does. Franklin's team found that early in life, the hippocampus is producing new neurons at an extremely high rate, a process called neurogenesis. This sounds like it should help memory. It does the opposite. Each time a new neuron gets inserted into an existing memory circuit, it can partially rewire the connections holding an old memory together, in effect overriding or destabilizing what was stored before. The infant brain isn't failing to save memories. It's aggressively renovating the storage system itself, over and over, before anything gets the chance to become permanent. Franklin's team tested this directly. They gave young mice a fear memory, then either sped up or slowed down their rate of neurogenesis. When they accelerated it, the memory vanished faster. When they slowed it down, the memory lasted longer than it normally would have. The rate of new brain cell growth wasn't just correlated with forgetting. It was causing it. This explains something that used to confuse researchers for years. Children don't slowly lose their early memories over decades, the way you might expect if the memories simply faded like an old photograph. They lose them fast, and early. Studies tracking children's own memories of events from ages 2 and 3 found that by around age 7, most of those earliest memories had already vanished, replaced by nothing, not even a vague impression. The forgetting isn't a slow decay across a lifetime. It's a sharp cliff that happens while you're still a small child, driven by a brain that is still being built. But neurogenesis is only half the story, because it explains why individual memories get scrambled. It doesn't fully explain why almost nobody, across every culture ever studied, can remember anything before roughly age 3.5. For that, researchers point to something else entirely: language, and more specifically, narrative structure. A memory isn't just a sensory recording. To become a retrievable, tellable memory, an experience needs to be organized around a self, a timeline, a sequence of cause and effect. A toddler doesn't yet have a stable sense of, "I was there," in the way a 5-year-old does. Psychologist Katherine Nelson, who spent decades studying how young children talk about their own experiences, found that autobiographical memory develops hand in hand with language, specifically the ability to talk about the past in conversation with other people. Children whose parents engaged them in detailed conversations about shared past events, asking questions questions like, what did we see at the zoo, and then what happened, developed richer, more durable autobiographical memories than children whose parents didn't. The scaffolding for remembering your own life, it turns out, is partly built through being asked to narrate it. This is why the offset of infantile amnesia lines up almost exactly with the emergence of a stable sense of self and basic narrative language, somewhere between 3 and 4 years old. Before that point, a child's brain is recording plenty. It simply lacks the architecture to file those recordings under a category called, my life, in order. Here's the part that should genuinely unsettle you. Those early memories aren't necessarily deleted. Some evidence suggests fragments may still exist, physically, somewhere in the brain, encoded but permanently unreachable, like a locked room in a house you've lived in your entire life, one you walk past every day without ever finding the door. In 2016, a research team led by Franklin used a technique called optogenetics on infant mice to test this directly. They tagged the specific neurons that activated during an early fear memory. Then, weeks later, when the mice showed no natural sign of remembering the event at all, the researchers used light to artificially reactivate those exact tagged neurons. The forgotten memory came back. The fear response returned in full. The information hadn't been erased. It had simply become inaccessible through any of the ordinary retrieval pathways a mouse, or a human, has available to them. If this generalizes to humans, and researchers are careful to note that it hasn't been proven directly, since you obviously cannot run this experiment on a human infant, it would mean the memory of your first steps, or the exact sound of your mother's voice on the day you were born, might still be sitting inside your brain right now. Not gone, just permanently locked behind a door your adult mind has no key for. Which raises an uncomfortable question about what a self even is. Most people assume their identity is built from the sum of what they remember, the accumulated story of their own life, stretching back as far as they can recall. But your life didn't start where your memory does. You existed, fully, as a conscious, learning, feeling being for years before the story you tell about yourself even begins. Whoever you were during those years, the person who first learned your parents' faces, who felt whatever a body feels the very first time it stands upright and doesn't fall, that person is gone in every way that matters for memory, and yet every experience you had then quietly built the wiring that everything after it was constructed on top of. You don't remember learning to walk, but your legs remember exactly how. You don't remember hearing your native language for the first time, but your brain built its entire architecture for understanding speech around those forgotten hours of listening. The self with no retrievable memories isn't a separate, discarded person. It's the foundation the rest of you was built on, invisible now, but load-bearing the whole way up. Somewhere in your brain, behind a door optogenetics can open in a mouse but nothing yet can open in you. There may be a record of the exact moment you first understood what a smile was, and who was making one at you. You'll never read that file, but it wrote you anyway.